All right, number 2. And you're talking about 1.2, right?
Yeah.
Okay. A child is 40 inches tall, which places her at the 90th percentile of all children of similar age. The heights for children of this age form an approximately normal distribution with a mean of 38 inches. Based on this information, what is the standard deviation of the heights of all children of this age? So when they give me this right here, when they give me a percentile, I can use that to find a z-score. So z is equal to x minus mu over the standard deviation sigma. I need to figure out what is the z-score for the 90th percentile. So there's a couple different ways you can go about doing this. You can look it up in table A, in the middle of table A. Or you can use inverse norm on the calculator. You're going to enter the percentile, so 0.90. Then you're going to enter the mean. For a z-score, the mean is going to be 0. And then the standard deviation. Again, this is for the z-score. These will be 1 and 0. So if I do that on my calculator, let me grab it and do it real quick. So to get to the inverse norm, that's second and vars. If you guys forget how to do some of those particular pieces, if you look on the calculator, to get to any of the things that are written in yellow above the buttons, that's when you push the second key. So if you look at the vars key, right above in yellow, it says DISTR for distribution. That's where we go for all of our distributions. So inverse normal is option number 3 there. I want 0.90 and then comma, mean of 0, comma, standard deviation of 1, close my parentheses. I get 1.28 if I take it out to just 2 decimal places. So 1.28, there's my z-score. Is equal to, x is going to be the observed value, and mu is going to be the mean. So a child is 40 inches tall. That's going to go in for x. So I have 40 minus the mean here. It says the mean is 38 inches. So 40 minus 38 over sigma. And now I can use some basic algebra to finish this out. I'm going to multiply both sides by sigma. So that'll cancel my denominator, so I'd have 1.28 sigma equals, let's see, 40 minus 38 would be 2. And then I just divide by 1.28. And that would give me my sigma. So 2 divided by 1.28 is 1.5625. So then I come over here to my choices. 1.56 inches right there. Yes.
Okay, so I did the and when I got mine, I got the 1.291 because I was gonna ask, this is 0.90. I did one that was 0.9015 to 0.8997.
So 0.8997. So the thing is, you want to find the one that is the closest to the decimal that you have. So 0.8997 is 0.0003 away from 0.90, and that other one was a little bit farther away. So that's why I went with the 1.28. Although I'm thinking if you do this with the 1.29 as opposed to 1.28, I was going to say it's going to be so close that you're going to be able to figure out which one it is. So if you look it up on table A and you're off by just like a 0.0 something, you're probably going to be fine. Yes.
Okay, so every time you're looking for the z-score and you're using the inverse norm, the mean will be 0 and the standard deviation.
Yes. If you're looking for a z-score, yes. Absolutely correct. Yes.
Can you do the next question, the 1.3?
Yep. A large set of test scores has a mean of 60 and a standard deviation of 18. If each score is doubled and then 5 is subtracted from the result, the mean and standard deviation of the new score are. So for new mu, we're going to do 2 times mu minus 5. Standard deviation is going to be almost the same. New sigma, we're going to do 2 times our old sigma, but we don't do any addition or subtraction with standard deviation because standard deviation describes how spread out my data is. If I double it, it's going to get wider. If I divide by something, it's going to get narrower. But adding and subtracting is just like moving the number line underneath it. It's not going to make it wider or narrower. So we would do 60 times 2, so 120 minus 5, so 115. So we're going to be able to get rid of these 3 here. And then standard deviation of 18, that would be 36. I would definitely be on the lookout for problems like this where you're transforming pieces. They will put like the common mistake on there as an answer choice. What else do you guys want me to go over? Yes.
I just want to know why 1.5 is not D.
Why 1.5 is not D. For a biology project, you measure the weight in grams and the tail length in millimeters of a group of mice. The equation of the least squares line for predicting tail length from weight is predicted tail length. So predicted tail length would be y hat is equal to 20 plus 3 times x, where weight is the x. Predicted tail length, or you could say tail length hat. I wrote it out as an equation, almost like slope-intercept form, but when you are writing a least squares regression equation, this is the preferred way to write it out with the words in there so that nobody has to guess what your variables mean. If you use x and y, please make sure you put a hat on the y, and then you've got to explain what those pieces mean. Which of the following is not correct? The slope is 3. That is the slope, which indicates the mouse's predicted tail length should increase by about 3 millimeters for each additional gram of weight. This one's correct, and I want things that are not correct. Predicted tail length of a mouse that weighs 38 grams is 134 millimeters. So I have tail length hat is equal to 20 plus 3 times 38. Oh, goodness. 20 plus 3 times 38. And we get 134. So it can't be this one. By looking at the equation of the least squares line, you see that the correlation between weight and tail length is positive. That is absolutely true because it is a positive slope. If the slope is positive, the correlation is positive. If the slope is negative, the correlation is negative. If you had measured the tail length in centimeters instead of millimeters, the slope of the regression line would have been 3/10 or 0.3. In centimeters instead of millimeters, yes. That one is also correct. Because if I measure a tail length and it's 2 millimeters, that is the same as 0.2 centimeters. So this one is correct. Mice that have a weight of 0 grams will have, right there, that is my tip-off. This is not saying it's predicted that they will have. This is saying every mouse that weighs 0 grams, which first of all is not possible, but let's imagine for a minute it is. We have a mouse that weighs 0 grams, and they are guaranteed always to have the exact same tail length every single time. This is deterministic language, so this is not predicted. I would definitely make sure that whenever you're talking about regression equations, that if you are going to, if they ask you to find, like, how long will the tail be for a mouse that's 38 grams? You're not going to come back and say, a mouse that weighs 38 grams will have a tail that's 134 millimeters. They're predicted to. We know that there's variation in all different populations. It might be longer, it might be shorter. We know there's this relationship. So I'm guessing, educated guessing, that it's going to be around 134 millimeters. Does that help? Yes. 1.9, absolutely. Before he goes to bed each night, Mr. Klein pours dishwasher powder into his dishwasher and turns it on. Each morning, Mrs. Klein weighs the box of dishwasher powder. From an examination of the data, she concludes that Mr. Clean dispenses a rather consistent amount of powder each night. Which of the following statements is true? All right, so consistent amount of powder each night. There we go. Well, when he's using it up, the amount of detergent is going to go down day after day. So this one is not correct. So anything over here that says statement 1, I need to throw out. So it can't be A and it can't be E. A scatter plot with days since purchase as the explanatory variable. Explanatory variables go on the x-axis. And total amount of dishwasher powder used as the response variable, so that's my y-axis, would display a strong positive association. We just said a minute ago that it's not going to have a positive association because as the number of days goes up, which we have as our explanatory variable, the amount of dishwasher powder, if he's using it every night, is going to go down, 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 down. So it is not this one. So anything that has 2 in it has got to go. So I'm left with number 3, but let's read through that. The correlation between the amount of powder left in the box and the amount of powder used should be very close to -1. This is a strong negative correlation. Negative correlation would mean as days go up, amount of powder goes down. Correlation doesn't tell me what the slope is. It only tells me the direction of the slope, whether it's a positive slope or a negative slope. Correlation, if you want to think about these numbers more like percentages, it's telling you how closely the data matches your line of best fit. So -1 tells me it's got a negative slope, and it is almost 100% fit to that line. If I were to graph the line and plot the data, those dots are going to be landing on or very close to it if I have a -1 correlation. Yes, Eni? It says that 1.9 is B, 2 only, D. 1, 2, and 3. High positive correlation. 2 and 3. Scatter plot with days since purchase as the explanatory variable. Oh, sorry. Yep. Amount of powder used, not amount of powder left. My apologies. So if I was plotting how much got used up, not how much was left over. My apologies, guys. See, got to read carefully or else you make stupid mistakes like I do. There we go. So my reasoning for this would be more days equals more powder used. Thank you for catching that. What else would you guys like to see? Yes. 1.13. The frequency table summarizes the distribution of time that 140 patients at the emergency room of a small city hospital waited to receive medical attention during last month. Which of the following represents possible values for the median and IQR of wait times for the emergency room last month? Okay, so we have our frequency. So basically what this is showing me is if this is less than 10, and then 10 to 20, this isn't the perfect way to make a dot plot, but I want to illustrate what's going on here. 20 to 30, 30 to 40, 40 to 50, 50 to 60, and then 60 to 70. All right, so my frequency table tells me where my dots are going to go. So less than 10 minutes, we've got 5. One, 2, 3, 4, 5. And then 24, so this is going to go up much higher. I'm not going to do every single dot on here. 45, this one's going to go up even higher. Then 38, 19, 7, and 2. So this is the basic shape of my distribution. Sorry, I drew all over that. And I don't have enough room or time to make all of those dots. What I can do, though, is see how many people they're talking about here. So looking at this, I'm going to add those to find total number of people. All right, so let's do that real quick. So 5 plus 24 plus 45. Never mind, it says 140. I'm not going to waste my time here. 140 patients. So the median would be the 70th person, right? Between the 70th and the 71st, since we've got 140. Median is half. So it's going to be median is going to be right in here. So I need to figure out where the split between the 70th and 71st person is. So if I do, 45 plus 24 plus 5. If I add these up right here, that's 74. And there's a whole bunch of people sitting right here. So the 70th person and the 71st person are going to be somewhere in that really tall bar, right? So my median is going to be at least 20, but less than 30 minutes. So let's look over here. At least 20, but less than 30. Less than 30. These are all more than 30. So I've got it narrowed down to choices A and B, and now I need to find my IQR. To find IQR, we do Q3 minus Q1. So I'm going to find that really similar to how I estimated where the median was. If there are 140 people, I'm going to divide that into quarters. I get 35. So I'm going to go 35 from each direction. Well, if I add these two right here, that gets me at 29. So the 35th person is going to be somewhere in this group too, right? Here's the 35th person. And if I do 140 minus 35, Q1 person, the Q3 person is going to be the 105th person, so 35 backwards from the end. So if I want to find the quarters, I'd go from the beginning to the 35th person, that'd be Q1. From the end backwards 35, that would give me Q3. So let's look at where person 105 would be. Here's 7, 9. That only puts me at 28. So the Q3 person is going to be in here. So now I'm going to look at what the difference is between these. So these people are more than 20 but less than 30. These people are more than 30 but less than 40. So if I subtract those, even if I look at the largest possible thing, from 20 to 40, that's only 20 minutes difference between those. If I do the lower end of Q1 and the upper end of Q3. So IQR is at most 20 minutes. (40 minus 20). This one is too big. So option A. That would be my best guess. If the Q3 person fell in the option that says at least 40 but less than 50, then I would have chosen B. Because that would have to be at least 20 apart, as much as 30 minutes apart. So the IQR would have to be somewhere in between 20 and 30. What else do you guys want to talk about and look at? Yes.
For number 10, what's the difference between a systematic random sample and a stratifying random sample?
So systematic random sample, you have a system for picking the people. Specifically, you have a numeric system. So for example, every 5th person. You said between that and stratified? Stratified random sample, you divide the population before choosing based on some criteria you think might be a confounding variable. Then choose some from each of your groups. So an example for this one would be maybe gender or age ranges. If you think gender is going to affect things, or age range, or socioeconomic status. Or neighborhood. If you think that one of those characteristics is going to change people's responses, like you think, let's use gender. You think that the men are going to be overwhelmingly answering similar to each other, and the women are going to overwhelmingly be answering similar to each other. And so you want to make sure that both of these groups get some representation so that you can see what the whole group together thinks. But you also get to see, am I right about this? Do the men's opinions differ on average from the women's opinions? And then I would know whether or not that's a confounding variable. If they both come out the same or about the same, like it turns out that the men answered about the same as the women, then I know it's not a confounding variable. Does that help a little bit? Okay. Yes. 17, absolutely. Still 15. 17. In retail stores, there's a lot of competition for shelf space. There are national brands for most products, and many stores carry their own line of in-house brands too. Because shelf space is not infinite, the question is how many linear feet to allocate to each product and which shelf, top, bottom, or somewhere in the middle, to put it on. The middle shelf is the most popular and lucrative because many shoppers, if undecided, will simply pick the product that is at eye level. A local store that sells many upscale goods is trying to determine how much shelf space to allocate to its own brand of men's personal grooming products. The middle shelf space is randomly varied between 3 and 6 linear feet over the next 12 weeks. And weekly sales revenue in dollars from the store's brand of personal grooming products for men is recorded. Here is some computer output from the study along with a scatter plot. So I'm going to be getting a lot of information from up here. And I'm going to look at the graph too. They have shelf length down here on the x-axis. So this is my explanatory variable. And they have sales over here on the y-axis. And this is the response variable. Describe the relationship between shelf length and sales. So this is where we would do Duffs. We're going to describe the direction, any unusual features, the form, and the strength. Some of this I'm going to have to get from the graph. Some of it I'm going to get from that box of information up there. So first thing I noticed looking at the picture, kind of looks like this. From left to right, the data is increasing. So I would say it has a positive relationship. Are there any dots that like stand out as being really weird, not fitting the pattern? So I would say it has no unusual features. What about the form? What's it most look like? What shape? Linear. And then our strength, this is where I'm going to look at R. I don't have R from the output, but I do have R squared. So I'm going to do the square root of R squared, 98.2%, so 0.982. I got 0.99. So I didn't write this down, but always, always, always get your context in there. Bless you. So I would say the relationship between shelf length and sales and I'm going to put my units in here, shelf length in feet, and sales, which is dollars, is a strong R equals 0.99 positive linear relationship with no unusual features. So that's how I would answer part A. Part B. Write the equation of the least squares regression line. Be sure to define any variables you use. This is if you use X and Y. If you use X and Y, you got to say off to the side, here's what my X means, here's what my Y means. I'm getting what X and Y are from the graph. Here's my X, here's my Y, but I would never, ever, 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 ever leave it like that when I am defining my variables. I always use words. That is the standard way to do it in statistics. We do Y equals, I think it's A plus BX is the way it's listed in the calculator. Y-intercept comes first, which is different than in algebra. And then B is our slope. So my regression equation is going to be sales hat. You could also write predicted sales, but the hat means predicted. Sales hat equals. Now I need my y-intercept. That is the constant. So 317.94. If they give you the data, take it all the way out to as many decimal places as they give you. I'm not going to put the 0 on the end, but I am going to take it out as far as the digits that are significant there. We have a positive linear association, so I'm going to have a plus. I can also find that by looking right here where it says shelf length and then coefficient. Here's my slope. 1.5268. I see that that's a positive slope there, so that, oh, sorry, not 1.52, 152.68. got my decimal in the wrong spot. Positive slope, positive association. And then I need my X variable in here that says shelf length. If it makes you more comfortable, you can write y hat equals 317.94 plus 152.68x. But then you have to explain what your x and your y mean. And in this case, your y would not mean sales. Your y would mean predicted sales. Make sure that whatever that response variable is, when you're writing about the regression equation, that is the predicted amount. All right. If the store manager were to decide to allocate 5 linear feet of shelf space to the store's brand of men's grooming products, what is the best estimate of the weekly sales revenue? So I'm going to come back here. I'm going to grab my equation. And I'm going to substitute in 5 linear feet. They're giving me shelf length here. So I'm going to put 5 in here. So 317.94 plus 152.68 times 5. And then I'm popping that right in my calculator. And I got 1081.34. So this is the predicted sales. At that level. Right, how many parts do we have to this? Of course, it's E parts. Let's see how far I can get. D, interpret the value of S. So S, they give us right here. S is equal to 22.9212. And interpreting S, pull this out and see the exact language that we used when we were studying this. There we go. Sorry guys, I'm not trying to waste time. I want to make sure that I'm getting that language exactly as we used it before. Thank you. I was going to say I can't find it right now. Thank you. There we go. Standard deviation of the residuals. So I would say the actual sales is typically about 22.9212. That's dollars. Away from the predicted sales from the least squares regression line. All right. Sorry, I wanted to make sure I was copying that language down and then I couldn't find it. And then with our last little bit, thank you, dear, identify and interpret the coefficient of determination. Coefficient of determination is r squared. Can I steal that packet for just another minute? There you go. This tells how much of the variation is because of the linear relationship. So about 98.2% of the variation in sales is due to the linear relationship with shelf length as represented by the least squares regression line. Have a fantastic rest of your day, guys. I will see you tomorrow. Bye. Have a good